We'll now discuss the next phase of the compiler process, which is code generation. Once the compiler completes the semantic analysis, or checking the parse tree and making sure that all the branches are semantically correct, the compiler then is going to go through a second pass over the parse tree. But this isn't to determine the correctness, because we already did that, but it's to produce the translated code. So each branch of the parse tree represents an action, which is a transformation of one or more grammatical objects into other grammatical objects. So the compiler must determine how that transformation can be accomplished in machine language. And this is the step that we call code generation. To help explain this process, we'll work through an exact example using the parse tree for the assignment statement x equals y plus z, where x, y, and z are all integers. So here's the parse tree for it. So we see that x, y, and z are variables, and then we use the same rules that we did before when we were talking about parsing. So y would end up becoming an expression, and an expression plus variable becomes an expression, and then variable equals expression groups up to an assignment statement. Typically, code generation begins at the productions of the tree that are nearest to the original input tokens. The compiler would then take each production and one branch at a time would translate the production into machine language operations or data generation pseudo-ops. So, for example, if we have the branch of the form y becomes a variable, so the y arrow variable, so think of the branch where we have like a y and then it goes down to a variable, we can actually implement that by allocating space for the variable y using the .data pseudo-op. So it would become just the y and then .data 0, just like the pseudo-op we've used before in assembly language. Now, in addition to generating the pseudo-op, the compiler must also build the initial semantic record that's associated with the non-terminal variable. So, I mean, for this particular case, the semantic record would contain, at a minimum, the name of this variable, which is y, and its data type, which is an integer. So then identical operations would be done for the branches of the parse tree that produce the non-terminal variable for symbols x and z. So once we've done that for x, y, and z, we would get the following code. So these would be the pseudo-ops for variables x, y, and z in our assembly language. Now, there are some branches that don't generate any machine code. So like, for example, the production that transforms the non-terminal variable generated from y into the non-terminal expression doesn't generate code. This just renames a non-terminal to avoid the ambiguity problem that we've discussed before. So, I mean, this demonstrates an important point, that although most branches of a parse tree produce code, some branches don't. And although no code is produced, the compiler must still create a semantic record for the new non-terminal expression in this case. And these semantic records would be identical to the ones that were built for the terminal variable, or I should say the non-terminal variable, excuse me. Let's now address the expression portion. So where we had the expression plus a variable, and that would turn into an expression. So that branch of the parse tree can be translated into machine language using assembly language instruction sets that we've talked about before. So the compiler would load the value of expression into a register, add the value of variable, and then store the resulting expression into a temporary memory location. So we can do this type of conversion by using the load, add, and store operations in the instruction set. So the names used in the address field of the instructions are determined by looking in the semantic records associated with the non-terminals of, in this case, would be expression and variable. So we basically use these operations, and to determine the address fields, we would just look up the information in the semantic records. So then this will result in some code for the branch, and we're going to need to have a temporary memory cell. So the results is going to be stored in this temporary variable, which usually the compiler will call temp. And so whenever the compiler generates one of these temporary variables, it must also generate memory space for it using the data pseudo-op. And then not only do we have to do that, the compiler needs to record the name temp and the data type, which in this case is an integer, of the result in the semantic record associated with the new non-terminal that's called expression. So here's the resulting code that we would get in our example, where if we're in this case, we're adding y and z together. So we would load y, because remember, we got y from the semantic record. We would add z to it. Once again, z came from the semantic record for z. And then we would store that in a temp. So remember, we would use the data pseudo op to create a temp variable, and we would take the result of y plus z and store that in temp. And as we just mentioned, we would have a semantic record for this temporary variable as well. So the name would be temp, and the data type of it would be integer. We can now address the final branch of the parse tree, where we build the non-terminal called assignment statement by having the production a variable equals expression, where in this case it would be x equals temp. So what we can do here with this production is we would translate it using load and store operations. So the way we would do this is we would load the expression that's on the right-hand side of the assignment statement, and then we would store it in the variable part on the left-hand side of the statement. So we're just basically using these load and store operations on the left and the right-hand sides of this assignment operator. And once again, the names names that are used in the address fields of the machine language instructions are obtained from the semantic records associated with the variable and expression non-terminals. So we would generate some code for loading the temp and then storing the value of x. And once again, the compiler must build the semantic record associated with the newly created non-terminal assignment statement. So here the name x and the data type integer of the variable on the left-hand side of the assignment operator are copied into the semantic record, and this is because the value that's stored in that variable is considered the value of the entire assignment statement. So this is the resulting code we would get for translating this part of the parse tree. So we're just basically loading what's on the right-hand side of the assignment operator, which is temp, so we load that, and then we're going to use the store operation on the left-hand side of the assignment operator. So we just have store x is all we need to do. And once again, we get temp and x from the semantic records from the variable and expression non-terminals. So this is the final result if we put the entire code together, all those pieces we've talked about together. So we have data pseudo ops for x, y, z, and temp. So the first part would take care of the adding part. So this is our addition part right here. So we would load y, add z, store that in the temp, and then this part right here takes care of the assignment portion of the statement. So we would load temp into a register, and then we would store that result into x. So this takes care of the addition of y and z, and then storing that into x.